Imagine you have this incredibly brilliant, I mean, just absolute Michelin star chef working in your kitchen.
Okay, I like where this is going.
Right. So every single night, this chef invents an absolute masterpiece of a recipe. Just a perfectly balanced, incredibly complex dish. But there is a massive catch.
They completely refuse to write the recipe down.
They will not write a single thing down, not one note.
Yeah, that would be a nightmare.
It totally is. So the very next day, when a customer comes in and asks for that exact same dish, the chef just looks at you blankly, pulls out all the raw ingredients again, and just starts blind tasting and guessing their way through the whole process from scratch.
Which is brilliant, but it's incredibly frustrating.
And highly prone to mistakes. And the crazy thing is, that amnesiac chef is exactly what dealing with today's smartest AI agents is like. I mean, they can solve wildly complex problems, but they instantly forget how they actually did it.
They really do.
So, welcome to the deep dive. Today, our mission is exploring a state-of-the-art paper out of Carnegie Mellon University. It's titled Inducing Reasoning Primitives from Agent Traces, and it essentially cures this AI amnesia we're talking about.
It really is a foundational building block.
Right.
Because it addresses this massive flaw in what we call open-ended React agents.
Right.
And just to set the stage for those of you who might not spend your days looking at AI architectures, a React agent is designed to reason and act in this continuous loop.
Basically talking to itself, right?
Exactly. You give it a goal, and it says, thought. I need to find this information. Action. Search the web. It reads those results, forms a new thought, takes a new action.
And they are incredibly capable when they do this.
They are, but like your chef analogy, every single time they face a new multi-step problem, they reinvent their entire reasoning process.
So all that brilliant logic just vanishes.
Gone. The successful routines they come up with are trapped in these temporary scratch pads, and they just get entirely discarded the moment the problem is solved.
Okay, let's unpack this. Because if you are relying on an AI to, say, manage your calendar or analyze legal contracts or even allocate a workforce, you cannot afford an agent that is just guessing its way through every single time.
Oh, absolutely not.
You want a reliable, standard operating procedure.
Right. You want consistency. And that is exactly why this matters for you, the listener. This paper asks, what if the AI could automatically mine its own past successes to build a reusable library of reasoning skills?
A permanent library.
Yes. And to understand how they fix this amnesia, we really have to look at how the researchers extract these hidden routines without any human hand-holding.
Because humans aren't writing the code here.
Exactly. Historically, if you wanted an AI to follow a strict workflow, a human engineer had to manually map out every step. It takes massive amounts of domain insight. But here, the researchers introduce a concept called reasoning primitive induction.
Reasoning primitive induction. Got it.
It's a single-pass method. It looks at a corpus of successful past agent actions, clusters the recurring thoughts, and synthesizes them into a compact library of what the paper calls pseudo-tools.
Wait, pseudo tools. Is this like, okay, taking a video game analogy here, is this like watching 1,000 hours of someone playing a fighting game, isolating the exact combo moves they used to win, and then just mapping that entire sequence to a single hotkey?
That is actually a really great way to look at it. Yes, but taking that analogy even a step further, the AI is discovering those ultimate combo moves completely on its own.
Wow.
No human is sitting there telling it what the combo should be. The researchers laid this out in a 4-step pipeline. They call it Algorithm 1.
The mechanics of that pipeline are super fascinating. Walk us through it. Step 1 is the filter, right?
Yeah, step 1 is the filter. You start with a massive data set of the agent attempting to solve problems.
Yeah.
And you just filter out all the failures.
Just toss the bad runs entirely.
Exactly. You only look at the traces where the AI actually got the right answer. Then step 2 is extraction.
What are we extracting exactly?
You take those successful runs and you strip away all the messy actions and observations. You get rid of the web search results, the database queries, all the formatting noise.
So you're just leaving the inner monologue.
Right. You just keep the natural language thought strings. It's purely the cognitive steps it took to get to the finish line.
Okay, so we have a giant pile of winning thoughts. What's step 3?
Step 3 is categorize and merge. You actually have a large language model look at this massive list of successful thoughts and group them into categories.
Because it's probably saying the same thing 100 different ways.
Exactly. It looks for synonyms and themes, and it narrows thousands of messy thoughts down to maybe 5 to 10 canonical categories.
That makes sense. And then step 4.
Step 4 is top case synthesis. The system takes the most frequent categories, usually the top 5, and transforms them into typed Python stubs with natural language doc strings.
Okay, wait, I need to pause there. Typed Python stubs with natural language docstrings sounds a bit heavy.
It does, yeah.
If I'm picturing this, it's basically creating an empty coding container, right? The code itself doesn't really do anything, but it has a plain English sticky note attached to it,
A sticky note for the AI, exactly.
telling the AI, hey, this is exactly what this specific tool is supposed to accomplish when you call it.
That is the perfect way to visualize it. It's a structural wrapper around a natural language instruction.
Give me a concrete example. I know the paper had that MUSR murder mystery subtask.
Oh yeah, the MUSR benchmark.
Yeah.
It evaluates multi-hop reasoning. So the AI reads this complex narrative and has to figure out who killed a character named Jimmy.
Poor Jimmy.
Right. And the suspect list includes characters with overlapping alibis and motives, like Isla and Randy.
And without any tools, the AI just kind of flails around.
It really struggles because it tries to hold the entire mystery in its head at once. It reads that Isla was at the bar, Randy saw Isla at the park, someone had a motive, and it just gets tangled up in all the facts.
It's like a bad detective.
Totally. But as algorithm 1 watches the AI occasionally stumble into the correct solution, it notices a pattern in that inner monologue we extracted.
The winning thoughts.
Yeah. The successful runs always feature the AI saying things like, let me search for specific evidence about Randy's alibi, or I need to verify Isla's motive.
So it's identifying the actual detective work.
Exactly. So the synthesis step grabs all those scattered thoughts and turns them into a permanent pseudo tool. They literally named it investigate evidence.
I love that. And what does the sticky note say on investigate evidence?
The docstring gives a specific instruction. It tells the AI to analyze the narrative, extract the means, weigh the motive, evaluate the opportunity, and flag any conflicting witness statements.
So you build this customized, highly specific library of reasoning tools. But the real test is what happens when you hand that library back to the very same AI that struggled in the first place, right?
And that is the big aha moment of the paper. The results completely break our assumptions about AI capability ceilings.
Hit me with the data.
The staggering part is that the induced libraries drastically outperform the exact same agent that generated the traces.
Beating its own baseline.
By a lot. They tested it on the Rule Arena NBA subtask. The AI has to apply incredibly complex collective bargaining agreement rules to figure out if a player trade is legal.
Which is notoriously complicated.
Oh, it's a 5-kilobyte rulebook in his prompt. Without the tools, the agent's accuracy was 30%.
30%. Oh,
With its own self-discovered tools, accuracy jumped to 74%.
wait, 74? That's a 44 percentage point increase on the exact same model.
It is massive.
Yeah.
And it wasn't just the MBA task. On the MUSR team allocation task, where it has to assign people to projects based on soft personal preferences, it jumped from 38% to 68%.
Another huge 30-point leap.
Yeah. And on NatPlan, which is a meeting planning benchmark, it went from 7% to 29%.
Okay, those numbers are wild.
Yeah.
But what's fascinating here is the underlying mechanism driving that leap. The paper talks about this idea of implicit aggregation.
Yes, implicit aggregation. Think about the original agent facing that NBA rulebook. It's trying to reconstruct the logical steps for applying a trade exception entirely on the fly.
Just guessing as it goes.
Right, which is high variance and super prone to failure. But the synthesized tool looks at the corpus level success.
The wisdom of crowds.
Exactly, but the crowd is just past versions of itself. It creates this perfectly stable, reliable subroutine based on all its past wins.
Okay, I have to play devil's advocate here for a second because something isn't fully adding up for me.
Sure, go for it.
If the AI is just reading a natural language docstring for the tool, just a sticky note, instead of executing hard, deterministic Python code, isn't that literally just a fancy prompt? Why is that so revolutionary?
I get why you'd ask that, but it's actually a profound difference. We can't write a clean, deterministic Python script for a human concept like verify Libby consistency or analyze team allocation.
Because it's too nuanced.
Way too nuanced. Code is rigid. A Python script only understands 0 or 1, true or false. But binding an LLM to interpret a docstring at the exact moment of invocation allows the AI to execute fuzzy, logic-based reasoning moves.
So it retains the fluidity of natural language but packages it into a subroutine.
Exactly. Traditional code simply cannot handle that kind of human nuance.
That makes a lot of sense. It's one thing for an AI to beat its own messy past using fuzzy logic, but it's an entirely different thing for it to beat a system meticulously designed by human engineers.
And that is exactly what happened. This is a story of discovery versus design.
Walk us through that. Did they actually test it against humans?
They did. These automatically discovered libraries matched or actually surpassed expert-authored, hand-designed decompositions.
Meaning humans sat down, mapped out the best way to solve it, and the AI still won.
Yes. For instance, on that MUSR team allocation task we mentioned, the AI's self-discovered tools beat the human design pipeline by 17 percentage points. On the NatPlan meeting planning, it beat human design by 15 percentage points.
Why are human experts failing here? We supposedly know how we plan meetings.
Because human engineers naturally default to building rigid sequential pipelines. We think, okay, parse the data, then plan the schedule, then check for errors.
A straight line.
Right. But tasks like scheduling and team allocation are full of soft constraints and weird trade-offs. The AI discovered that reasoning isn't a straight line.
It's messier than that.
Much messier. It requires flatter, more flexible moves like rearranging partial constraints simultaneously, things that human designers just didn't anticipate.
Here's where it gets really interesting to me. The AI did all of this with minimal supervision.
Almost none, yeah.
When it started, it was given 0 domain-specific tools. No special NBA rule checker, no murder mystery tool, just generic search and lookup.
Just to the basics.
And it essentially invented its own domain expertise out of thin air, purely by practicing.
It really is a paradigm shift. But I know what you're probably thinking next.
Oh, I guarantee I know what any skeptical listener is thinking. Whenever an AI paper claims massive improvements, like a 44% bump, the immediate question is, are they just throwing an absurd amount of money and computing power at this?
The brute force question.
Yeah. Let me guess. To get that NBA accuracy bump, they just ran the model 100 times for every question and burned a hole in the server farm until it got lucky.
Nope. The math completely debunks that.
Really? So it's not just massive compute?
Not at all. First of all, reasoning primitive induction is actually about 24% cheaper per instance than its closest multi-step competitor, which is a framework called agent workflow memory.
Wait, cheaper?
Yes, 24% cheaper. And second, the researchers actually tested that brute force approach you just mentioned.
They ran a control test.
They did. They ran a self-consistency control where the model just guessed 20 different independent times and took a majority vote.
So that's using what, 21 times the compute?
Exactly. And that brute force method still scored 9 to 24 points lower than the induced library.
Wow. So throwing servers at it didn't work.
Pure compute does not equal better reasoning. Structure does.
That is a massive takeaway. And speaking of compute, did they only test this on those giant trillion parameter models?
Actually, no. That's another great point about generalizing. They didn't just test it on massive models like DeepSeek V3. They ran the exact same pipeline on a much smaller, weaker model.
Which one?
Gemini Flashlight.
Okay, a very lightweight model.
And it successfully induced its own libraries and boosted its own performance. It saw an 18-point jump on that MUSR murder task, for example.
If we connect this to the bigger picture, this means the technique is completely model agnostic.
Totally model agnostic.
You can apply it to lightweight, local AI models and make them punch vastly above their weight class.
Exactly. You don't need a supercomputer to see these gains.
Okay, we have seen the triumphs, and it is incredibly impressive. But to give you, the listener, the full picture, we have to look at where the system breaks down.
Because it's not magic, it does have limitations.
Right. What does this mean for real-world deployment? I know the paper mentioned an arithmetic issue.
Yeah, the arithmetic Achilles heel. There were specific failure modes on the Rule Arena airline baggage fee calculation and the tax computation tasks.
Taxes and fees. Notoriously math-heavy.
Right. Because the tools rely on LLM interpretation of a docstring rather than deterministic code, long chains of strict arithmetic just compound small errors.
Because LLMs are basically predicting text, not doing hard math.
Exactly. So the method falls completely flat here. It actually dropped below the baseline zero-shot chain of thought.
So how do you fix that?
It requires a hybrid system. You need to route the actual math to a hard-coded Python helper calculator while keeping the fuzzy logic for the reasoning steps.
That makes sense. Now, there is another limitation here, and honestly, I think it's a fascinating broader impact.
The bias trap.
Yes, the bias trap. Because the tools are written in plain English, they are highly auditable, right? You can literally read the AI's thoughts and edit the docstring.
Which is great for transparency.
It is, but there is a real danger. The AI learns by aggregating successful past traces.
Right.
Well, what if the AI was using a systematic bias to guess the right answer in that training data?
Then that bias gets synthesized and permanently hard-coded into the new reasoning tool.
Exactly. So what does this all mean for you listening right now? If you are at a company and you decide to train an AI on your company's past successful decisions,
You have to be incredibly careful.
you really do. Are you crystallizing your best practices, or are you just automating your hidden biases?
Hmm.
If your successful projects always involved overworking the junior staff, the AI might just encode burn out the juniors as a permanent pseudo tool.
It's the double-edged sword of trace induction. It learns exactly what you show it, flaws and all.
So to quickly recap our journey today, AI agents can now essentially cure their own amnesia.
They can mine their past successes.
Build those pseudo tools, vastly outperform their own baseline capabilities, and even beat human-engineered logic.
All while staying auditable and compute efficient.
It is a massive leap forward. But I want to leave you with one final provocative thought to mull over.
And this is the really wild part.
It is. We've talked entirely about AI today. But if an algorithm can perfectly distill successful reasoning moves from thousands of messy, varied thought processes, what happens when we apply this trace induction not to AI, but to human workplace data?
Imagine pointing this exact algorithm at your company's Slack channels.
Or your email histories for successful projects?
Could an AI extract the hidden reasoning primitives of your most brilliant employees?
Right. Could it identify the exact cognitive moves that lead to success better than the employees themselves ever could?
Extracting the Michelin star chef's recipe without them ever writing it down.
It is entirely possible, and it's something to think about as these systems get smarter. Thank you for joining us on this deep dive. As always, keep questioning the information around you, and we will see you next time.